One says calculate the formate ion concentration and pH of a solution that is 0.05 molar formic acid, and 0.10 molar HNO3. So we have two substances, two solutions in the container. Now, remember what we looked at yesterday. You always want to label everything first. So formic acid is an acid, because it says so, but it's not one of the 7 strong acids, so we're going to label this weak acid. Remember that anything that is weak exists at equilibrium. So then think about what HNO3 is. Hello? No, she's at home today. It's a cold day. Yeah, yep, fine. So HNO3 starts with a hydrogen, so it's an acid, and this is one of the 7 strong acids. So since HNO3 is a strong acid, that means it's a strong electrolyte, which means when it gets put into water, it breaks apart into H plus and NO3 minus. So here we have a weak acid and we have a strong acid. Once you've identified your substances, once you've labeled them, write out the equilibrium for the weak acid or the weak electrolyte. So formic acid is HCOOH. And it says calculate the formate ion concentration. So that tells us that we're probably looking at formic acid. We have H plus. HCOO minus. Doesn't really matter how you write it. I just want to write it technically the correct way. The H gets pulled off of the oxygen because oxygen is the more electronegative atom. So we have this weak acid that's at equilibrium. Because this is technically in water, we're just not showing that plus H2O. So if we need to do any calculations with something that is weak, we need an ice table. Now we look at what we have in this container. We have 0.050 molar formic acid, but we also have 0.1 molar HNO3. Now because it's a strong electrolyte, what we actually have are these ions that are in the beaker. So I don't see NO3 minus in here anywhere. NO3 minus is a spectator ion. So I actually wrote the spectator ions up on the board yesterday. The NO3 minus is a spectator. It's always a spectator ion. It means it just floats around in solution, doesn't participate in the chemistry. However, H plus, we have H plus here as well. H plus is actually the common ion. So that means initially we have 0.1 molar H plus. We have 0 formate ion. Now, that's all we know, so I'm going to use x's. Minus x plus x plus x. So we have 0.05 minus x, 0.1 plus x, and x. And so since these are at equilibrium, we can plug them into the K expression. Since this is a weak acid, it's producing H plus. That means this is Ka. And so Ka is products, which is H plus times HCOO minus over HCOOH. Now you might look at this and say, well, I don't have the Ka value. No, but you do have Appendix D. So if we find formic acid in Appendix D, formic acid has a Ka of 1.8 times 10 to the negative 4th. Again, I just looked on Appendix D for formic acid. 1.8 times 10 to the negative 4th is Ka. And then we just plug in all of our values. 0.10 plus x times x over 0.05 minus x. Again, on tests, on quizzes, College Board is not going to require you to use the quadratic formula. And so to prevent the use of quadratic, you just have to make sure that you're writing your assumption down. We're assuming x is small. So since we assume x is small, that allows us to actually neglect this minus x on the bottom and this plus x on the top. So we're assuming that x is such a small number, it's not going to drastically impact the H plus and the formic acid concentration when we're plugging it into Ka. And so once we have our Ka expression, we can go ahead and solve. So I'm going to multiply 0.05 over, and then I'm going to divide by 0.1. And I get a value of x to be 9 times 10 to the negative fifth. 9 times 10 to the negative fifth. Now go back to the question and see what it wants, because in number 1 it actually wants two things, wants two answers. One of them is the formate ion concentration, and one of them is the pH. The pH can come from H plus at equilibrium. So formate ion concentration is X, so I'm just going to put molar as my unit and just label it HCOO minus concentration. And then the pH. If in your calculator you do 0.1 plus your 9 times 10 to the negative fifth, if you keep it to 2 sig figs, like the problem, even 3 sig figs, it's still 0.1. So to find the pH, we need the negative log of H plus. Normally we would do 0.1 plus x, but even when I add x, when I add 9 times 10 to the negative fifth, it's still 0.1. pH equals negative log of 0.1. So we get pH, that's 1 times 10 to the negative first, so pH is 1. So this is a pretty acidic solution, which actually makes sense because even though we have a weak acid, look at the concentration of the H plus that's coming from the strong acid compared to the concentration of the weak acid. We have H plus that's coming from the strong acid, so the pH is 1. So the number 2 is going to be similar. So see if you can go through and work through number 2, kind of like we did in number 1. So in number 2, you're calculating the fluoride ion concentration and pH of a solution that's 0.2 molar HF and 0.1 molar HCl. This is what people miss the most. Is HF a strong acid? No. HF is a weak acid. A lot of people will look at this and say, well, I have 2 strong acids. No, we don't. HF is weak. HCl is strong, which means when I put HCl into water, it breaks apart into H plus and Cl minus. But because HF is the weak acid, that's what's going to exist at equilibrium. Let's see who said this. And then you can find hydrofluoric acid on Appendix D as well. So work through this, take a couple minutes, set up your ICE table, use number 1 kind of as a guide because it's very similar to number 1. But see if you can work through, because you'll see questions like this on mastering, right? The common ion questions on mastering. I got X to be 0.00136 by plugging into Ka. So this Ka value came from Appendix D. Remember, as you're working on mastering, to use Appendix D if they don't give you the Ka. And in mastering, it actually says, use Appendix D for the equilibrium constants to find, and then it gives you a problem. So you find Ka, you also have Kb values on the back of Appendix D. So if it's a base, you have Kb values as well. You can assume X is small, so we get F minus. Now technically, we should do 0.1 plus X. So our H plus concentration that we actually plug in, if you want to do 3 sig figs, is 0.101. But in this case, H plus, when we add X, right, it's not nearly as small as what it was in number 1. Now, if you do 0.1, would you get the same pH? Yes, approximately. But just remember that at equilibrium, it's plus X. So I take the negative log, and if you use this entire number, 0.10136, you actually get a pH to 2 decimal places because of 2 sig figs. It's actually 0.99. Now, if you just did 0.10, your pH is 1. But again, that's why showing your work is important. So whether you're using 0.1 or 0.101, just make sure you're showing that work. pH is 0.99 or 1. Again, very acidic, which makes sense because although we have a weak acid, we're adding a strong acid in, which produces all of the H+. Any questions on the do now? I just wanted you to have a couple extra common ion examples. If you want to make yourself a note as you're working on mastering, you know, that today's do now was some common ion questions for you as well. So what we're actually going to do for today is we're going to look at pages 2 and 3 of the notes. So in your notes packet, if you actually just open to page 2, that's kind of the background information, and then page 3 are the examples that we'll get into for today. Today we're going to focus on acid-base neutralization. So we're going to review net ionic equations. We're going to review some dilution calculations. A lot of these kind of background concepts that we've seen before, we're going to put into acid-base examples. So we have a few examples that we're going to look at today. But again, this is the background information. So once we get into buffers and titrations, we've already covered this. So at the top of page 2 of your notes, there's a lot of background information. So it says when a strong acid and a strong base are mixed, they react, and here's the net ionic equation. So I have each one of them kind of simplified here. First and foremost, and this is at the bottom of your page, when you mix an acid and a base, doesn't matter whether it's strong or weak, when you mix an acid and a base, you always produce a salt and water. So you mix HCl and NaOH. You're going to create NaCl and H2O. You mix HF and LiOH. You make LiF and H2O. So whenever you add an acid and a base together, you always create a salt. Remember that a salt is an ionic substance. When we say salt, we don't mean NaCl. Could it be NaCl? Sure. But it could be a lot of other things as well. A salt is a soluble ionic substance. So we have 4 different possibilities with acid-base reactions, and this is showing the net ionic equations that go along with it. This is at the top of page 2. So we can have a strong acid and a strong base. So for example, strong acid, strong base could be something like HCl and NaOH. When we're looking at net ionic equations, and we're going to be reviewing net ionic equations not only today but also next week. When you're looking at net ionic equations, remember that strong electrolytes completely break apart. So strong electrolytes dissociate completely. So when we looked at net ionic equations, back from the summer work, right, chapter 4, strong electrolytes completely dissociate. Strong electrolytes are strong acids, strong bases, and soluble salts. Soluble salts will contain potassium, nitrate, ammonium, or sodium, and sometimes fluoride. The solubility rules that you need to know, that College Board requires you to know, are potassium, nitrate, ammonium, and sodium. Any salt with those 4 ions, one of those 4 ions will be completely soluble, will break apart completely. Weak electrolytes stay together. So weak electrolytes stay together. Weak electrolytes are weak acids, weak bases. That's it. Right, weak acids and weak bases. Remember, electrolytes are solutions, aqueous. So the third thing with net ionic equations is that solids, liquids, and gases always remain together. In order to break apart, it has to be an aqueous solution. Only electrolytes are aqueous solutions. Notice your acids, your bases, your soluble salts. If it's insoluble, like lead iodide, PbI2, that's insoluble. That means it's a solid. Solids stay together. Liquids stay together. That's why notice for all of these, H2O stays together. It's a liquid. So we're going to review net ionic equations and how strong acids break apart and strong bases break apart. And all we show in the net ionic is the actual chemistry that's happening. We can have a weak acid mixed with a strong base. Notice how your weak acid is staying together because it's weak. But the strong base breaks apart. And then weak base and strong acid. So weak base like NH3 and HCl. Weak base stays together, strong acid breaks apart. Again, you produce the salt and water. And then we could also see weak acids and weak bases. Now, we don't see that as often because those calculations get very complicated. So we usually stick with the first 3. Strong acids and strong bases are nice for us because notice how it's a single arrow. Single arrow, no equilibrium. Weak acids, weak bases, notice the double arrow. Equilibrium means we're probably going to have to use an ice table. So as we get into acid-base neutralization reactions and we look at the reaction that's occurring, it's important that we pay attention to what are our strong electrolytes, what are our weak electrolytes, is it breaking apart? Now at the bottom of your page, and the information at the top of the page we'll actually be talking about as we go through these examples. So instead of just reading through them, we'll hit on them as we go through these examples. You have this at the bottom of your page. This is kind of the mathematical operations that we use as we look at acid-base reactions. So the first thing, because acids and bases are solutions, right? We have 2 solutions that we're mixing together. That means that we're actually changing the volume. So the first thing that we can do if we added volume to volume is we can use the molarity equation, M1V1 equals M2V2. We can use the dilution equation to figure out what's the new molarity. What's the new molarity of the acid? What's the new molarity of the base? The reason that that's important is because we can use molarity in a stoichiometry problem. As long as we've taken into account that the volume is changing through dilutions, we can use molarity right in stoichiometry problems. So this is actually the order that we're going to do calculations in. If we're mixing an acid and a base together, we're going to start by using the dilution formula. M1V1 equals M2V2. We're going to figure out what's the new molarity of the acid, what's the new molarity of the base. Then we can do stoichiometry, because no matter what strength of acid or base you're mixing, a neutralization reaction is a stoichiometry problem. The reaction is going to proceed to make product until we run out of a limiting reactant. Now, the questions that we look at are one-to-one, so it's going to be relatively easy for us to figure out what the limiting reactant is. And then, if we have weak acids or weak bases involved, we have to end with an equilibrium problem. So we have to end with an equilibrium calculation. Typically, it asks us to find the pH. If it's a strong acid, strong base, the pH is based on whatever we have left over at the end. If there's anything weak involved, then to calculate the pH, we have to do an ice table, like what we were looking at before. So what we're going to do is we're just going to jump into an example, right? We're going to go through this within an example, and we'll kind of talk through this as we go. So on page 3, the top of page 3, we have this example. Determine the pH when the following solutions are combined. So the first thing that we need to do, first thing is identify these solutions. Identify them. Are they strong acids? Are they weak acids? Are they strong bases? Are they weak bases? Perchloric acid, HClO4. HClO4 is one of the 7 strong acids. So I'm just going to label that SA for strong acid. Potassium hydroxide. So hydroxide means it's a base. Look on the periodic table. Potassium is part of that lowercase b, so this is a strong base. So we have a strong acid and a strong base mixing together. Now, because we are mixing 2 solutions together, we are changing the volume. So if we think about what's happening, I'm just going to kind of draw it over here. So we have 35 milliliters of 0.2 molar HClO4 going into this beaker. We have 35 milliliters of 0.2 molar going into the beaker. But we also have 25 milliliters of a 0.25 molar KOH solution going in. So now instead of HClO4 being 35 milliliters, it's now going to be in 60 milliliters of solution. So we're changing the concentration. For KOH, instead of having 25 milliliters of 0.25 molar, we're going to have 60 milliliters, so we're changing the concentration. So the first thing we want to do is figure out what are the new concentrations. So we're going to start by looking at dilutions. So for the acid, since we're adding volume to volume, we need to use a dilution problem. Volume to volume, we're changing the concentration. So M1V1 equals M2V2. Remember, this is an equation that we're going to use a lot that is not on the equation sheet. So M1, I'm focusing on the acid right now, 0.2 molar. V1 is 35 milliliters. I need to find the new concentration when these two are mixed together. When these two are mixed together, the volume becomes 60 milliliters. Volume can stay in milliliters as long as the units are the same. Again, this is 60 because it's 35 plus 25. It's the two solutions being added together. So for M2, we do 0.2 times 35 divided by 60. 0.2 times 35. And since they had 4 sig figs here, I'll just stick to 4 sig figs. 0.1167 molar. The reason that we're doing this dilution problem is because since we're mixing the acid and the base together, doing the dilution is actually preventing us from doing moles back to volume, or back to molarity. So we can actually just figure out the dilution and then use that as a stoichiometry problem. So then for the base, let's do the same thing. M1V1 equals M2V2. So M1, 0.25, V1, 25. We're solving for the new molarity when the two solutions are mixed. So the new molarity of KOH, 0.1042 molar. So now these are now the molarities of the acid and the base when they react. These are the molarities of the acid and of the base when they react in that beaker. So now we've accounted for adding volume to volume. Now what we want to do is we want to look at the stoichiometry that's occurring. After we account for volume to volume with the dilution, we want to look at the stoichiometry. Now I want to review net ionic equations. So we have HClO4. Remember, acids and bases are aqueous. In an acid-base neutralization reaction, this is nothing more than a double replacement reaction. Neutralization is a double replacement reaction because to create a salt and water, hydrogen, so H plus from the acid and K plus from the base, replace each other. So we get KClO4 and HOH, which is H2O. Now I left my state of matter off of KClO4 for now. KClO4 is a salt. It's an ionic substance. If it has potassium, nitrate, ammonium, or sodium in it, it's a soluble salt, meaning that it's aqueous. Since it has potassium in it, it's a soluble salt. Now let's look at complete ionic and net ionic. All right, reviewing this from the beginning of the year. Aqueous solutions have the potential to break up. Solids, liquids, and gases do not, so they will stay together. Now, in order to break up, it needs to be a strong acid, a strong base, or a soluble salt. So we said this is a strong acid. This will break apart. This is a strong base. This will break apart. This is a soluble ionic salt. This will break apart. So what we can do is we can separate this into the ions. So we'll have H plus ClO4 minus plus K plus OH minus yields K plus ClO4 minus plus H2O liquid. It's soft to incorporate H2O, it just can't break apart. Now whatever is the exact same on each side of the arrow can cancel. Those are our spectator ions. So ClO4 minus is the exact same. That's a spectator ion. Means it doesn't participate in the actual reaction. It's just floating around in the beaker. So we have ClO4 minus just floating around in the beaker. K plus is also a spectator ion. It's K plus on each side of the arrow. So that means that K plus is also just floating around in the beaker. Those are our spectator ions, which means the net ionic equation here is H plus OH minus yields H2O. Here's our net ionic equation. This is the actual reaction that's taking place. Now we can look at the stoichiometry for this. I'm going to set up stoichiometry. I'm just going to write my amounts right underneath here. This is not an ice table. Right? It might look like I'm setting it up like an ice table, but I actually, when I taught honors, taught stoichiometry with what are called BCA tables, before, change, and after, which actually look very similar to ice tables. But it's just organizing the stoichiometry. Just organizing what you have. So if I'm looking at stoich, I'm looking at how much of everything we have. H plus was the strong acid. You have 0.1167 molar H plus. After they are put in the beaker, before they react, after they're put in the beaker, these are what their concentrations became. And I'm actually not worried about water because it's a liquid. Water is water in the beaker no matter what, no matter how much you have. Now, for the stoichiometry, right? Again, this is stoich. This is all stoichiometry. One of these is going to run out first. Yes, I know that we're using molarity. I know that we're using molarity and not moles. But you can use molarity because we've already taken into account the volume change. We're treating molarity just like moles. One of these is going to run out first. Now it's a 1-to-1 ratio. Which one's going to run out first? OH. All right, we're going to use up all of the OH minus. It's going to run out first. We have less of it. That's the limiting reactant. Well, if we're using up this much OH minus, we're going to use up the same amount of H plus because it's a 1-to-1 ratio. So I have 0 OH minus left over after the reaction. I have 0.0125 molar H plus left over after the reaction. So for strong acid and strong base neutralization reactions, the pH is based on what we have in excess. There's no equilibrium here. I don't have a strong acid or a weak acid or a weak base left over at the end. This is H plus. This is in excess. The H plus is excess. That's what determines our pH. If I take the negative log of this, this is the H plus concentration. So if I take the negative log, 0.0125, I could technically do 3 sig figs because of this number. You could do 3 or 4 decimal places. I get 1.903. So again, when a strong acid and a strong base are mixed, the pH of the solution is determined by whatever you have in excess. This was a stoichiometry problem. Right? This is what I had before the reaction. This is what happened during the reaction. OH minus ran out, so it was the limiting reactant. So the pH was based on the H plus that was left over. Could you do this differently and figure out your moles and do moles and then go back to volume or go back to molarity? You could, but doing this dilution helps to save time. So the point of doing the dilution first is before the reaction takes place. We're actually diluting the acid and the base. We're changing the volume. Then you can use the stoichiometry to figure out how much we have. This is a strong, strong neutralization. Questions on this before? Yeah.
Would the H plus ever be limiting reactant?
Could.
You can't take the negative.
Yes. So if H plus, let's say that H plus was the limiting reactant, and it could happen. If this was the limiting reactant and this ran out, that means that you would have a certain amount of OH minus left over. So then let's say that we had 0.01 molar of OH minus left over. Well, you can take the negative log of this. So if you take the negative log of this, right, of OH minus, that gives you POH, and then you can figure out pH, right, subtract from 14. Yeah. So yeah, you could have either H plus or OH minus in excess if you had more strong base. So if we had more OH minus than H plus, then we'd have OH minus in excess. We'd have to take the negative log to get POH, and then we would expect our pH to be up above 7. Yeah. Any other questions? So we're going to look at the next example. So this one is not a strong neutralization. So for this one, now we have hypochlorous acid and potassium hydroxide. So hypochlorous acid, HClO, and potassium hydroxide, KOH. So now let's think about first what type of substances these are. And then we'll go through the dilution, stoichiometry, equilibrium steps to figure out the pH. This is asking determine the pH when the following solutions are combined. HClO, just HClO. That is not one of the 7 strong acids. So I'm going to label that weak acid. Potassium hydroxide, we just said, was a strong base. So again, what I'm doing, draw it up here a little bit smaller, just so that I save us some space. In this beaker, I start by adding 35 milliliters of 0.2 molar HClO. I'm also adding in 25 milliliters of 0.25 molar KOH. So what I'm doing is I'm adding 35 and 25 milliliters together, so I'm changing the volume. When you add volume to volume, you start with a dilution problem. So I'm going to start up here with dilution. Dilution is M1V1 equals M2V2. Whenever you add volume to volume, you add 2 solutions together. Figure out what your new molarity is before the reaction takes place. So 0.2 times 35 equals M2 times 60. Again, the 60 is the 25 plus 35. It's the 2 volumes being added together. So we get 0.1167. And then we get 0.1042. Because again, this is 0.25 times 25 is M2 times 60. So we start with the dilution. We're adding volume to volume. So when we add volume to volume, we figure out what the new molarities are before the reaction takes place. Now let's look at the stoichiometry. We can start by looking at the net ionic equation. So if I write the full equation, it's HClO plus KOH. Neutralization will give us a single arrow. Acid-base neutralization reactions are always single arrows. That's why we're using stoichiometry. Produces a salt and water. So the salt will be KClO, and then H and OH will produce H2O. Now I know that water is a liquid. KClO, that's ionic. Metal and a polyatomic. Cation and an anion. Because it has potassium, it's a soluble salt. Dissolves in water. If it has potassium, nitrate, ammonium, or sodium in it, it dissolves in water. Now, if we want to write the net ionic, aqueous solutions have the potential to break apart. Liquids cannot break apart. So I draw the arrow just to tell me that those have the potential to break apart. In order to break apart, it needs to be a strong electrolyte. HClO, I'm going to put an X there. HClO is a weak acid. Weak acids stay together. KOH is a strong base, that breaks apart. KClO is a soluble salt, has potassium, nitrate, ammonium, or sodium in it, so that breaks apart. So I'm going to leave HClO together, because weak acids do not break apart very much. So they stay together as a molecule. Plus K plus OH minus yields K plus ClO minus plus H2O. So if we take a look at this, the only spectator ion that we have is K plus. All right, just K plus. So I'm going to rewrite my net ionic. HClO plus OH minus. Remember, ions are always aqueous. Yields ClO minus plus H2O. There's my net ionic. So I'll write net. It's important that you can still do net ionic equations. College Board always just wants net ionic. Now, we can look at the stoichiometry. Using the net ionic equation, we can look at the stoichiometry. What happens when these react? So, HClO, I'm going to use these M2, right, because the dilution, the results from the dilution, these are our values that we use in stoichiometry. So I have 0.1167 molar weak acid, 0.1042 molar OH minus. I don't have any ClO minus at the beginning. And H2O we don't care, because H2O is just a liquid in the container. Now, again, this is stoic, right? This is all stoichiometry. I'm just showing, I'm organizing my information for stoichiometry. Instead of having lots of dimensional analysis problems, I'm just showing the stoichiometry here. HClO and OH minus are a 1-to-1 ratio in this neutralization. So in order for this to go to completion, I need equal amounts. We're running out of one of them. We're running out of whichever one we have less of. In this case, it's OH minus again. I'm running out of OH minus. That's my limiting reactant. That limits how far the reaction can go. Because it's a 1-to-1 ratio, that means I'm also using up the same amount of HClO. But now on the opposite side of the arrow, I'm also creating that many products. This is showing what's happening in the stoichiometry. This is showing what's happening in terms of the moles. OH minus is being used up. Because it's the same ratio, we need the same amount of HClO, but we're producing the same amount of ClO minus. So I'm going to figure out my amounts really quick. Okay, so back to this acid-base neutralization reaction. So we had our stoichiometry set up. This looks very much like an ice table. I call them BCA tables when I taught honors. It is an ice table. It's just, since I taught it before, I taught ice tables because you didn't learn ice tables in honors. We labeled this before, so before the reaction takes place, the change during the reaction, and A for after the reaction takes place. Now, you do not have to label it BCA. You don't even have to show it like I do. It's just a way, a much more simpler way to represent stoichiometry. The biggest thing is that you have to keep in mind this is all showing the stoichiometry. OH minus ran out. That's the limiting reactant. So after the reaction, OH minus was used up completely. We had HClO and ClO minus left over. So unlike the strong titration, which only had H plus left, not titration, neutralization, which just had H plus left over because there were no products, it was just water. Unlike the strong neutralization, when you have one of them that is weak, you have to pay attention to what you have left over in the container. So after this reaction takes place, I just want to show it kind of as a picture here. After the reaction takes place, we have 60 milliliters of solution like before. The volume didn't change. But now what we have in this beaker is we have HClO and we have ClO minus. So we have HClO in this container, we have ClO minus in this container, and we always have water, right? Water is always in here. So we have a weak acid and its conjugate base. Now this is going to look like problems that we saw in the do now. Because for weak acid, strong base, the pH is determined based on what you have at equilibrium. So I'm going to draw a line right down here. Because in this beaker, we have something that is weak. We have the weak acid. We have to look at what this, like what's happening at equilibrium. So now we're going to look at the equilibrium part of this. We didn't look at equilibrium for strong because there was nothing weak left over at the end. So we have a weak acid and its conjugate base. So we're getting back into equilibrium, and that's what's going to determine the pH. So I have, in this beaker, I have a weak acid. Right, you could do plus H2O if you want. Or you could just do HClO. You can, the plus H2O is up to you. If you do the plus H2O, it looks like this with H3O plus and ClO minus. If you didn't do the H2O, you just have H plus Cl minus, which is fine as well. But the reason that we have to use equilibrium is because we have a weak acid and its conjugate base left over in this container. So now, it's exactly what we've seen before with ice tables. So in this beaker, that's represented by this equilibrium reaction. we have HClO, and we also have ClO minus. So initially we have 0.0125 molar HClO. Water doesn't matter because it's a liquid. Nothing about H plus or H3O plus in here. But we also have ClO minus. So after the stoichiometry, after the neutralization reaction has occurred, we have a weak acid and its conjugate base left over in the container. This is a common ion problem. We had a weak acid and its conjugate base. We have a common ion here. So now we go through just like what we did in the do now. So we set up our equilibrium, we fill in our ice table with X's. Hypochlorous acid, HClO, has a Ka value of 3 times 10 to the negative 8th. If you ask where I got that from, I just found this from Appendix D. On a test or a quiz, you would be given Ka or Kb values. So now we can use Ka, we can use equilibrium. The goal was to determine pH. All of this is just to figure out the pH after this neutralization reaction. So over here, 3 times 10 to the negative 8 equals. I'm not showing the expression. I know, shame on me, but I need to save some space. So my Ka expression is H3O plus times ClO minus over HClO. Assume X is small. By assuming X is small, we can neglect the minus X and the plus X. And now we can solve for X. Divided by 0.1042. 3.599 times 10 to the negative 9th. I think. Let me do this one more time just to make sure. Divided by 0.1042. Yeah. All right, so here's X. 3.599 times 10 to the negative 9. I underlined X here because that's H3O plus. To find the pH of a solution that's at equilibrium, you need the H plus at equilibrium. So if I take the negative log of this, and we stick to 4 sig figs because that's what we've had, so that's 4 decimal places. 3, 8. Now, do you have to stick to 4 decimal places? No. Could you do 2 or 3 and be okay? Yes. So the pH is 8.4438. Now, when we look at this and we're like, well, but we had a weak acid here. But we also had its conjugate base. The conjugate base concentration is almost 10 times. It is 10 times that of the weak acid. So we actually had a little more conjugate base. So the pH is basic. So these are the steps that we have to take when we have a neutralization reaction. Would we rather have a strong neutralization? Yes, because it's just stoic. Will we always have that? No, because why would we? So when we have any neutralization, we go through the same steps. use dilution first. Figure out what the new molarities are. Then look at the neutralization, look at the stoichiometry. If you have something weak left over, think about what is in the container. If you have something weak left over, then you have to look at equilibrium. This is a multiple choice question that's at the bottom of page 3. And you'll see that it says, which of the following is true if the solutions in the table are combined? The first thing I want you to do is take a look at the table. Label the solutions. Are they strong? Are they weak? Because that is going to help us with the math that we'll have to do. So you're looking at the acid and the base. I'm not sure why that just says acid. Just took a screenshot from the... All right, so we have two substances. HNO3 is an acid, starts with H. It's a strong acid, one of the 7 strong acids that we need to know. KOH is a base because it ends in OH. Hydroxide is part of that B on the periodic table. So we are combining these two solutions. When you are adding volume to volume, you need to look at dilutions. Find the molarity before the reaction starts. There's another teacher that says if you're adding volume to volume, you have to voom for like VM instead of M1 V1, M2 V2. She does it the other way. Whatever works. When you're adding volume to volume, find the new molarity. First thing we have to look at is dilutions. M1 V1 equals M2 V2. So M1 V1, we're looking for the new molarity when these are added. So 30 plus 70 is going to be 100 milliliters. So when these two solutions are combined, they're combining to become 100 milliliters. So the acid has a new concentration of 0.009 molar. The base has a concentration of 0.014 molar. Now think about the reaction that's occurring. I'm going to write it right under here. If these two are combined, an acid and a base will undergo a neutralization reaction to produce KNO3 and H2O. Now, if they wanted the net ionic equation, we have to break up strong electrolytes, so we'd actually break up these 3. However, we're not worried about the net ionic here. What we're worried about is which one we're going to run out of first. If I have 0.009 molar HNO3 and 0.014 molar KOH, which one's going to run out first? HNO3. HNO3, there's less. This is going to run out first. So HNO3 is the limiting reactant. That helps us eliminate 2 choices right away. HNO3 is the limiting reactant. I can eliminate A and B. Now it comes to finding the pH. So after these 2 are mixed, we're using up HNO3 completely. So we have to use up the same amount of KOH because it's a 1-to-1 ratio. So we have 0 left over of HNO3. And we have 0.005 molar left over of KOH. OH minus is in excess. So this is answering the question, can OH minus be in excess? So I'm going to just write it up. I'll write it over here. We have 0.005 molar OH minus concentration in excess. Because 0.005 KOH is the same amount of OH minus. Now we can find the pH of this. If I take the negative log of 0.005, this is OH minus. So what am I actually calculating here? pOH. So the pOH is 2.30. The pH, 14 minus that, is 11.70. So, between C and D, 11.0 rounds to 12. Right? So, again, this is looking at the idea. See how the strong after, these actually cancel out. If you look at the net ionic equation, it's just water on the product side. So there's nothing that's at equilibrium. There's no weak acid or weak base that's at equilibrium, which is why we don't need an ice table for strong neutralizations. This is going to help us as we get into titrations next week. You can see why if you haven't heard of the questions, the notorious Chapter 17 questions that take one period for one question. You can see why. There's just lots of steps. So I want to take a look at least parts A and B of this example. So if you actually flip in your notes to page 16, we're going to focus just on parts A and B for now. A and B are going to be nice and short, or should be nice and short. So this says a 0.599 gram sample of LiOH. So before you even read on, label LiOH. Has hydroxide, so it's some sort of base. Look at your periodic table, see if lithium falls in that B. It is added to 1 liter of a 0.05 molar solution of hydrozoic acid, which is HN3. So think hydrozoic acid. Is that one of your 7 strong acids? Label that. Assume the volume remains unchanged after the LiOH is added. So that means assume that it's still 1 liter. And then they gave us the Ka value for HN3, which we won't need right now because we're going to skip over part C for now. Part A says write the net ionic equation for the reaction that occurs. Okay, well, we have LiOH. Now, I know that it says you have a 0.599 gram sample, but it's being added into the solution. So we're going to say that LiOH is aqueous, because we have a solid that's going into the solution. So we're turning it into a solution. Plus HN3, hydrozoic acid. This is a base plus an acid. This is a neutralization reaction. Single arrow for neutralization. In a neutralization reaction, you have a double replacement reaction that occurs. So lithium is going to combine with N3 minus. It's a weird looking polyatomic ion. It's N3 minus 1, so this becomes LiN3 plus H2O. Water's a liquid. Now, I know lithium is not one of these. It could be. This is an AP practice question. Would they put lithium in here? No, it would probably be sodium. more than likely you would see sodium hydroxide. But this is a strong base. This is going to break apart. This is a weak acid. It's not going to break apart. LiN3 is a soluble salt. It is a soluble salt. Again, College Board would probably give you K plus or Na+. It's weird that in this practice question they gave Li+. But lithium, I mean, if you look on the periodic table, lithium is right above sodium and potassium. So it carries a lot of the same characteristics, a lot of the same properties. H2O is a liquid. So you break apart any strong electrolytes. So the strong base. The weak acid stays together. The weak acid stays together. This soluble salt breaks apart. Water stays together. These non-ionic equations are the equations that we've been seeing with the Bronsted-Lowry acids and bases. Because, notice now, Li plus is a spectator ion. We've been seeing examples like this. So if we rewrite this non-ionic equation, OH minus, which is aqueous, plus HN3, which is aqueous, yields N3 minus, which is aqueous, plus H2O, which is a liquid. There's our non-ionic equation. There's our answer for part A. And then part B says, determine the molarity of LiOH. Go back to the problem and read what the problem says. You can find molarity. You don't need an ICE table. You don't need stoich. A 0.599 gram sample is added to 1 liter. Think about your equation for molarity. Capital M. Molarity is moles per liter. Moles per liter. So figure out 0.599 grams, figure out how many moles that is. So Li plus O plus H. .948. So there's 0.0250 moles, and it says it's added to 1 liter. Easy enough calculation right there. 0.0250 molar. And again, we're going to skip C for now. We'll come back to that later. So this is just showing you how, really this was to focus on the ionic equation. Showing how strong acids, strong bases, soluble salts break apart. Weak acids, weak bases stay together as molecules, even though they're aqueous. Solids, liquids, and gases stay together. We're going to talk more about buffer solutions on Monday. But what we actually made in the second example, when we had a weak acid and its conjugate base, was called a buffer. So the point of a buffer, and this was in the video, and again, we're going to talk about this more on Monday. The point of a buffer is to resist pH changes. So we actually have a buffer system in our blood to keep the pH from changing drastically so that we don't die. So the pH is going to stay fairly constant for a buffer. And it's because we have an acidic part and a basic part. And we'll talk about the net ionic equations that go along with this and everything on Monday. We actually looked at these first two ways to make a buffer. Neutralization reactions. When you have leftover weak acid and you have its conjugate base, that's a buffer. When you have a weak base with its conjugate acid left over after neutralization, that's a buffer. We're going to look at ways 3 and 4 next week, but through neutralization, we create these buffer solutions. Now with a buffer, kind of some skills review. You'll notice on the board, the only thing I have for over the weekend is to work on questions 1 through 4 of mastering, and then to review any part of your last unit notes, unit 7. You need to make sure that you know conjugate acids and bases. So make sure that you know that HA, this weak acid, A- is its conjugate base. If you have a weak base, NH3, know that NH4+ is its conjugate acid. Because when we look at buffers, we see salts like this. Well, Na never participates in the chemistry, but the salt actually brings in the conjugate base. Make sure you can calculate pH, which hopefully we've been doing. Don't forget the idea that Ka times Kb equals Kw. And then, any neutralization that has a weak acid or base results in a buffer problem. And we'll look at this more next week, and we'll tie this in when we look at titrations as well. But these are just some background skills. So if you're like, oh, I don't really remember conjugate acids and bases, right, over the weekend, just look back at, I think it was the first video, 7.1, where we looked at conjugate acids and bases. If you need to look back, right, Ka times Kb equals Kw, that's on your equation sheet. So the only thing that I really said, like over the weekend, you can work on numbers 1 through 4 of mastering. That's common ion questions. You have some time, about 15 minutes. If you want to work on them now, you can. The other thing is the bonus. I uploaded the playlist, or I uploaded videos to the playlist yesterday, and I added the playlist to the stream of Google Classroom. So if you go into Google Classroom on the stream, I added the playlist that has the tutorial videos for the bonus. So I have 4 different videos. I work through each part separately. So you can watch all of them, you can watch none of them. The bonus is due March 3rd, so we still have plenty of time. But just know that there's really not much for you this weekend, so if you want to work on that, you can.